And welcome to another video that we're going to be showing you this week on static pressure and why is static pressure so important? Why is static pressure considered to be king? Well, static pressure controls everything, and it is something that is very sensitive and something that every unit needs to have set up and tested, no matter if it's a brand new install or an existing unit. Now, the what is static pressure, you may ask? Well, static pressure is essentially air resistance. It's a forced air HVAC system with ductwork, relies on air being pushed through the ducts to circulate warm or cool air. But various factors inhabit that airflow. So the force pushing the air must be stronger than the resistance, which is i.e. 90s or no turning vanes, deadheads, duct boards, vertical rises, etc. So the forced air pushing the air, or the force pushing the air, which is your blower motor, must be stronger than the resistance in the ductwork that's caused by the 90s and the turning vanes or deadheads or duct board or etc. It's impossible not to have any resistance at all, but the ideal is to keep it in check, much like your blood pressure is. An HVAC professional can account for air resistance by measuring pressure drops at specific points in the system. From there, they can tell you if there's a problem and hopefully what's causing the problem. Perhaps one of the most frequently ignored factors in setting up the duct system is the external static pressure, or what we're going to call for short ESP. In the measurement of all the resistance in the duct system, the fan has to work against. Examples are filters, grills, AC coils, and the ductwork. It is the sum of the suction pressure, which is negative, and discharge pressure, which is positive, created by the equipment blower, which is your blower motor. So as the blower motor pushes air out, it has to suck air in to be able to push it out. It can only push out what it's taking in. So you got to understand these units do not make air, they're moving it. Blowers move air throughout the system and are designed to overcome restrictions in the system external to the equipment, such as system components and ductwork. They are rated for giving a CFM at maximum external static pressure on high speed. So understand, we're not creating air, we're just moving air from one side of the house to the other side of the house. If you dump 1400 CFMs into a building, you have to return 1400 CFMs. If you do not, then you have high humidity issues, and that will feel like heat. So there's a lot of reasons why we have to get all this stuff done and do it right. So external static pressure is measured using a manometer, and it's expressed in inches of water column, i.e. WC. The airflow rate, or CFM, of a motor is directly related to the external static pressure. The higher the external static pressure, the lower the CFM. The lower the external static pressure, the higher the CFM. High static pressure readings indicate that there is excessive resistance in the system. This may be caused by dirty filters, dirty evaporator coils, closed dampers or closed grills, restricted supply or return grills, or undersized ductwork. If you know the external static pressure, then you can determine what the CFM is. And now I'm going to repeat that. If you know what your external static pressure is, you'll be able to determine what the CFM is. Just because you have a 2-ton unit doesn't mean it's always going to blow out 800 CFM. Keep that in mind. Proper static pressure will allow your system to deliver heated and cooled air optimally. This translates into lower utility costs, less failure of expensive parts, and greater comfort in your home. High static pressure is the leading cause of compressor failure and X13 motors. High static pressure can reduce your cooling efficiency SEER rating by 50%, and high static pressure can reduce your capacity by 40 to 50%. That will probably shock you, and we will recap some of this in a little while, but we're going to show you exactly why this is. Now, when we're going to check static pressure, you have a couple of options. Now, we carry Fieldpiece at Ed Supply, so we have the Bluetooth version for those that like to go cordless and like to have quickly if you're crawling under a house. This is kind of pretty cool. Here you've got shorter tubes right here, magnets right here that stick to the ductwork. These are really good. You got to have your cell phone and you got to download the job link to be able to use this manometer this way. And this one is the kind of like the step above. It's a digital, it's step above from the analog, the old analog. And you'll see these here. This is for checking your gas pressure and your gas valve with these yellow hoses. What we're going to use is that white hose, and we're going to use these duct ports here. You cannot test your static pressure properly without this in ductwork, okay? This here is for your gas pressure. This part is for your ductwork. So now I use this one quite a bit more than I do these over here because I can see what's going on pretty easy where I don't have to use my phone. I can actually have it in my hand and see it. So we're going to go through how to install this and get this right. So these are the duct probes that we was talking about. They're magnetic here. And on the face of that, there's an arrow that lines up with this probe. So there's an arrow pointing this way because that probe is pointing that way. But you'll drill a hole in the ductwork, put this will go in, and there's a magnet here that will snap to the ductwork. And you point the arrow here, which is facing the same as that, into the airflow. Your tubing goes here and goes into your dual manometer. So now we want to look at, this is a gas furnace. You have your blower motor here, you have your heat exchanger here, and you have your separate coil on top of that. And then we have this return plenum. Now, I call this a deadhead system. This is probably one of the most common things because when you're using a furnace, you have to allow for the coil on top of that. And you have here, this is one of the most common installs. You always see a filter right here on the side of these furnaces. And you see you have plenty of ductwork, it looks like here. So we're going to see there's a few issues going on with this install. Now, when you're checking your static pressure with the dual manometer that we showed you, you will have a couple of test ports. So the furnace, which is this part here, this blower and this section here, this is rated from the factory to have an external static pressure. Now, they don't take in consideration your coil because that's separate. It's considered an accessory. Anything separate from the actual furnace is considered an accessory. So the static pressure that you read on your panel is just for this space here. And then you have this to worry about. You have this deadhead to worry about. And you have these takeoffs to worry about. You have this filter to worry about. And you have this 90 degrees here to worry about. All these are going to cause issues with your static pressure or issues, turbulence, let's say. So let's say if you had an invisible line, you would see, or if you had if we could see air, you would see air coming back here, swirling up here, making its way through this filter, going in through this blower motor, coming out, going through the coil here, hitting this and coming right back and hitting the air that's coming back and forth until it starts to do this number and it pushes its way out through the ductwork. Now, so you want to be able to test all these. So you need to do a test port in your furnace right here and right here. All right, so in the blower housing itself, on the other side, leave the filter in place, check it here and check it here, and you can use that reading for your heating reading. And then you also want to come up here. So technically when I'm doing it and there's no space right here, I don't want to risk drilling a hole in my furnace or damaging my heat exchanger because this reading here would definitely be different here if that's a wet coil. Dry coil, it's going to be kind of close. But I want to see what my unit and my coil's doing as one, because if you have an air handler, the coil's already in the air handler. So I like to test mine here and right here. The reason I'm testing it here is because this right here is what the actual resistance right here, this area right here, is the exact resistance of what that blower motor is going through. And I want to make sure of that because, and it's going to go over this coil. So here is the external, and this is the external here, of what that unit is actually going to deal with. So I'll put a probe here, and I'll put a probe here. Now, this right here, you can do to say, okay, let's say I have a high return on this side, and if I drill a hole and put it here and I see a huge drop, then I know this filter's dirty. It's just as easy to pull it out and look. You know what I'm saying? So But if you wasn't able to, or couldn't get it, or didn't have access to it, and you needed to confirm that filter is dirty, you could do that with that pressure drop reading there. But to me, that's just another way of doing it. You could really just pull it out and see if it's dirty. But what they're getting at is if it's dirty or if it's too thick for that airflow. The other thing is, let's say this is a 5-ton drive, okay, and this is the only return we have. Well, those are 25 by 16 notches on a furnace. 25 by 16 will carry 2,000 CFMs until you put a filter in there. And when you put a filter in there, everybody that does heating and air ought to know what a 25 by 16 return grill carries. About 2 ton, maybe 2.5 if you're lucky. You just choke this 5-ton down to 2.5 by putting a filter right there. Now, if this was a 5-ton, you'd have to have this same setup on this side of the furnace or coming out underneath it. So if you got a 5-ton drive and you're only getting 2.5-ton return, you got to have another 2.5-ton here. So you got to keep that in mind too. And then we have this deadhead up here. So when we go back here in just a few minutes, we're going to look at that dual manometer, and I'll show you how to read it. But I want to go for now, drill a hole here, put P1 here, drill a hole here, put P2 there, and then you're going to add those numbers together, and we'll see what it comes up with. So on this drawing, we kind of done that, and you can see here's our return. If you could see the airflow, it's coming in hitting here, but because we have a radius throat and a radius heel, not a lot of hitting and building up. It's going to actually flow around these corners, all right? So you're going to have less drag and resistance coming down, less drag and resistance coming in here. We're still going to put our probe right here in the side of the furnace. You don't have to do in the door. You can put it in the side. If you want to, you can put it in the door, but it needs to be on this side of that filter. And then here was where we were talking about in that coil. This is actually a true reading of the filter, of the furnace, but I want a reading like right here, okay? But you can see what they're doing here. They did one up here in the return of the supply, and they got a 0.15. All right, they did it here, right here at the coil, and they got a 0.27, and they done it here, and it was a total of 0.42. So it was these two basically added together is the same you're going to get here. So you can look at this if you wanted to get real particular and see if your coil's dirty or if your coil's clean without having to tear it apart and open it and look at it on the inside. You could actually do that by static pressure. Put a probe here, see what the difference is, and you'll know real quick if that coil's dirty or not. And we'll show you how to read that. But that's going to give you a supply of 0.42. Now, over here on the return, you put a probe in here, and you got 0.16, which is great for this. And then you come down here to your filter, and you have a 0.21 in the filter area, but your total return is 0.37. That's really high for a return. So that lets me know we have issues right here because we've just choked down our return here. Now, you see these numbers, they got 0.37. That was your return. Even though you have a negative, it will be a negative sometime. It will be a negative number because that's a return. Okay, so keep that in mind. But we're not going to use it as subtraction. We're going to add it. So you take the supply, 0.42, you add it to the 0.37, and you get a total static pressure of 0.79, or you'd round it up to 0.80. So if you look at your chart in your install manual, it would tell you would go to whatever size model that return is, or that unit furnace is, find out what speed tap you're on. Let's say we're checking this in AC. So if we're checking AC, this coil is going to be wet. It's going to have a little bit more resistance on a wet coil than you will a dry coil. So you want to keep that in mind. But if we're testing it here, you're not catching that. You're not getting this wet coil. You have to test it up here on this side to get that wet coil. So you got to understand that. If I'm going here, it would be during a heat session, okay, where this would be, not equivalent unless it's dirty. But that's why I just check them up here, because it's usually easier. This is where the air is coming out of that, and I want to check right here and see if I've got a dirty coil or I've got resistance. And you'll be able to see that. See this number here, this is 0.42. Now, on a supply, you want to look at 0.3. This needs to be a 3. You'll see 3 up to maybe a 5. Keep that number in mind. This, see where it's 0.3 is, this should be more like a 0.1 or a 0.2. When you get into 0.3s, you've got resistance and that return needs to be fixed. And then we'll show you, so if I'm looking at this number here, I know I'm a little high here on my supply, but I'm really high right here. So if I could get this 0.37 down to 0.16 just by removing this filter, I'm going to be up here at the 0.16, and then you add 1/6 to the 4.2, and you see you got 0.58 or 0.6. So you see how much I gained just by doing that and taking that filter out. So then you go into, let's go with the proper steps of how to actually check it. So here's our furnace. There's our blower motor. Here's our evaporator coil. And we've got a filter here. So this one is a different system. You're coming in through the return, and it's pulling air across that coil instead of blowing it through it. So we want to go in, and what they want, run system in cool or heat mode, whichever is higher airflow. On an ICP, you need to really look at this because they will come from the factory with a AC tap on usually 2, and your heat tap will be on 4. Now ICP and a air handler, an FEM4 or a FJMA, those 3 and 4 are the same RPM. 2 is medium, 3 is high, and then 5 is for a high static condition. So let's say we're going to put the pin in 3 or 5. We're going to test this in cool mode because the higher the fan speed, the higher the static pressure is going to be. Okay. So then we go on here to where we see this is a minus and this is a plus. We're going to put our manometer here and a manometer here. They're using the Bluetooth, Fieldpiece Bluetooth for this. 0 a dual port manometer. It's the first thing you need to do. Once you got your tubes hooked into your probes, you 0 it out. All right, then you stick the P1 into the return and supply duct directly above or below the furnace or fan coil. 2 single port Bluetooth manometers mapped for positive and negative pressures respectively would work as well. And on the Fieldpiece, they have one negative is red and the blue is as supply. And you can do it positive, negative. You'll see when you actually have that they do blue is the supply is positive and red is the negative or the return. So I want to go in here now. There's a couple of ways you can do this. I always like to go dead center of the ductwork because that's where my airflow is going to be, because air comes out of a fan in a circular motion. So if you're testing down here in the corners, you're going to get a false reading because you're not in the airstream or the jet stream of that blower motor. So I always try to get dead center of the ductwork. Okay, locate in the center of straight duct run away from turns or other turbulent areas. Like I said, you're going to have turbulence down in here. You want to go right dead in the center because that's where that airflow is going to be at. Then you get down on locate in the center of a straight duct run away from the turns or turbulent areas before the unit and after the filter. It would do no good if I checked it here because the filter is a resistance. I want to test the airflow here, what that motor's doing, on the back side of that filter, not on this side, on the back side. Just like on the furnace, you want to test it in the blower motor compartment as it has already passed through the filter. If you're testing it on the air side of the filter, not the blower side of the filter, you're not getting any resistance reading what that motor is under. And I want to know what is that motor under, because that restriction that motor's under is going to determine how many CFMs that unit or furnace is putting out. So then we got the hose on the side of the probe should be perpendicular to the duct walls. That means parallel, or see how this pointed this way? It's also perpendicular with the ductwork. Pro tip should be in position and parallel with the airstream. Whether you're upstream or downstream makes no difference. Just make sure it's parallel with it. Basically pointing in the airflow. The difference between the positive and negative pressures. Now, they have the Fieldpiece Bluetooth dual manometer. That's what you see here. And they will show up as a minus 0.15. And the positive will be on this side. And when you add those together, you get 0.30. Okay. Sometimes you flip it around and it'll zero this out like they were subtracting each other. You don't want that. You've got to have that added together. All right, and then you look at here, the proper step. Make appropriate adjustments to the ductwork fan speed system, cleanliness, etc. to achieve a targeted TESP, which is total external static pressure and target airflow. So TESP is the pressure reading of the balloon pressure, which is your resistance inside the ductwork. In other words, there are essentially two types of pressure inside a duct system. There is velocity and static. If you look at the ductulator and you look at your friction rate, that's what that 1.0 or 0.80 that everybody sets their ductulator at to size their ductwork, that is not your static pressure. That is your friction rate. Friction rate determines velocity, and then your velocity and your friction rate will determine your static pressure. So you got to understand that just because I set that ductwork at 0.10 doesn't mean my static pressure is going to be 0.1. Just because I set my ductwork at 0.80 doesn't mean my static pressure for my unit is 0.80. That's just a friction rate. What 0.10 does is that is designed of all our ductwork, our metal that we have, our ductwork metal and our transitions are all set up on the 1.0 system. So let's say a 2-ton has 800 CFM. Well, if you look at your ductulator on 1.0 velocity and see what 800 comes down to be, it's going to either be a 12 or a 14 or whatever. 14 carries 1,000 CFMs. That's for your 2.5-ton systems. And then you have your 16s, your 18s, and your 20s. And when you look at those numbers on the 0.1 of the ductulator, you're going to see I can get my 2 tons, my 2.5, my 3, my 3.5, and my 4 and 5 tons spaced out that way. Now, where the 0.80 comes in is it's going to give me a bigger return, which is great. But if you look at your ductulator, you'll see where your return may call for a 14.5 or a 15. We don't make 14.5-inch flexor pipe, and we don't make 15-inch flexor pipe, so you'd have to go up to 16. So you could do it, that way too, and go 14 supply, 16 return, and on a 16 supply go 18 return, 18 supply go 20 return. Now, if you get to where you're going too big, you let too much airflow come through, you're going to cause another effect that we'll get into later. But the TESP is a pressure reading of the balloon pressure inside the ductwork. So now velocity pressure is the speed of the airflow. So velocity is the speed of the flow of air, and you can measure it by placing a sampling tube, which was the other piece in that dual manometer. There is a clear tube with a black fitting. You can put that in the ductwork, and that will get directly into the airstream, and that will let the air blow inside the tube to be measured. Static pressure is different because it is the pressure that pushes up against the outer walls of the ductwork. This friction is caused by air moving through the ductwork. Remember I said the friction rate is that we usually size our ductwork at 1.0 friction rate. That's what this is. Then you have coils, dampers, filters, etc. Static pressure is measured in inches of water column. Now, when a data tag tells us what the design total external static pressure is for a piece of equipment, it refers to the static pressure measured across just that appliance. So the fan coil or of air handlers, this includes the coil and blower assembly. Nothing else, not the return boxes, not the return filters, none of that. All that's considered extra or an accessory. When placing static pressure tips in the ductwork for fan coils, the tips should be located between the filter and the cabinet on the return side. That means come after the filter, before the cabinet, or in the cabinet before the blower motor, and between the cabinet and the rest of the supply duct. So you could have it. Some of the contractors now put a 3 or 4-inch piece of metal between the furnace and the A coil, and that is so they can measure the static pressure. Now, let's say ICP says it's measured or it's certified at 0.2 in heat. That is from the return before the coil. And that's where you need to make sure that thing is set till you get the optimal CFM that motor's blowing out. Now, for furnaces designed with a total external static pressure does not account for the case cooling coil. The case cooling coil is considered an accessory, and it has its own design pressure drop. So when you measure total external static pressure on the furnace, the measurements will be taken between the filter and the blower and between the heat exchanger and the case coil. Many contractors are now, like I said, installing a case coil with 3 to 4 inches of sheet metal spacing to allow a test port to be drilled without the worry of drilling into the heat exchanger or anywhere else on the cabinet of the appliance. It's always a good rule of thumb if you're building the ductwork and you're able to do that, you can actually put that in between the cabinet itself and the actual coil. So you want to keep that in mind as you're designing your ductwork. Once the measurement is completed, take any necessary action steps to make corrections to the ductwork, components, or airflow settings in order to improve overall system performance and air distribution. Another way to use the manometer beyond the total external static pressure is to measure the pressure drop across specific components like the filter, the coil, duct transitions, or etc., and you can actually pinpoint exactly where the problems are in regarding the diagnosing the high static pressure. Total external static pressure is one of the most versatile measurements that you have available to us as technicians. It's also the most misused. Be careful about probe placement and always be sure to use the appropriate plugs for the test ports before leaving the equipment. Put a piece of mastic tape if you don't have the plugs. Make sure you tape your holes up. And we'll go over to kind of show you things you can do. Like you can determine if a coil is dirty without having to take the sides of it off and actually crawl in there and look up in it, or rip open the flex and stick your head up in there to test that, and then worry about trying to get the flex taped all back up. You can do that with static pressure plugs. Now, these are important points to consider, and we went over this just a while ago, and I'm going to kind of slow it down just a little bit more to recap this. But proper static pressure will allow your system to deliver heated and cooled air optimally. If you have less resistance, your furnace has to work less as hard. I don't even know if that's proper English, but it's not going to run as long. Let's say, for instance, if I'm looking down here at this number and I can reduce my capacity by 40 to 50%, I have seen a house, brand new house, everything was built brand new. They put a 2-ton unit in because they needed 800 CFMs. So they put a 2-ton furnace in, put it in, set everything up, left it. Never checked anything else. The homeowner was very aggravated because during the heating season, the unit would not keep up. The unit ran all day long. It wouldn't get hot enough in the house, and they were complaining about it. So we went to look at the unit, and we got there. We checked our static pressure, and what we found was the blower speed on AC was low, was in medium. So we moved it up to hit 5 is what I had to be able, and then we took our static pressure reading and we looked at the install manual chart, and the chart told us at that static pressure reading that in AC we were blowing out 850 CFMs. That's great. 2-ton. We did the same thing in the heat mode, but what we found out was in heat mode, that system was only putting out 445 CFMs. 445 CFMs. What that means is I just reduced my capacity between 40 and 50% because my static pressure was off. So now in heat mode, I just had 1 ton of air in that house. No wonder they were complaining. And then they had a 5 kW heat kit, so it was only producing 64-degree air. So now you can see why the homeowner was upset. So what can you do at that point? Because there's not a tap for heat to go into that 5. Now you could speed the fan up. At that point, you would have to put a bigger return. So they had 14-inch flex, and it was kinked up pretty bad. So they had to go in and put 16-inch flex in, get the kinks out of it, pull it tight, stretch as tight as they could, refasten it, and then recheck your static pressure. Every time you make an adjustment, you got to check static pressure. So just because you take 14 off and put 16 on it and walk away doesn't even mean you're right. You may have to adjust your fan speed at that point. So you got to look at that and see. But it will. So you look at that unit ran nonstop because it's 440 CFMs in a house that needs 800. So it's going to run. What that's going to do is that's going to run a higher light bill. All right. But also you're putting a lot of pressure on the compressor and a lot of pressure on that X13 motor. Here's why I say this. You got to understand these units. A compressor is a pump. Okay. If you've ever cut one apart and taken them apart like we have here, and you will see it's a magnetic motor with the windings get electrical charge and cause an electrical field that causes a magnetic rotation on that motor. So as long as it's got power, that motor's turning, which means that compressor's pumping. All that compressor knows to do is pump. What happens is if you don't alleviate the heat that is caused from that, which is the heat removal of the house, all right, that pressure has to go somewhere. So if a fan is slowing down, you're going to cause overheating of the compressor, and it's going to go off on internal overload. And over time, when you do that, the windings get hot and they cool down, get hot, cool down, get hot, cool down. Eventually, they pop on the inside and they'll touch the case and ground the compressor out. Or sometimes they'll blow the pin out. They get so hot. And it's all because the airflow either in the house was not strong enough or set right, or the resistance was too high and the blower motor could not pull that pressure off of the coil, or your condensing fan motor. Just because it's brand new doesn't mean that condensing fan motor is pulling enough RPMs to get the heat off the furnace or off the coil. Or let's say your condensing coils are dirty. This is the same problem. That's why your capacitors will go out. That's why the condensing fan motors go out. That's why compressors go out. Coils are dirty or the fans are not doing their job to pull that heat off. Just keep in mind, as a compressor is pumping, causes heat. Heat has to be relieved. How do you relieve it? Airflow. Okay, so like in a blower motor, if the blower motor stops on the inside, that coil's going to freeze, which has no airflow coming across it. That's resistance. Okay, so if my blower motor's not blowing enough, then my coil don't get too cold to freeze. I have airflow going across it, and I don't cause resistance. So you got to keep those things in mind. So then we look at it's the leading cause for compressor failure in X13 motors. It also will reduce your cooling efficiency SEER rating by 50%. Right? Because we're looking at it's half the CFMs it's supposed to be doing, and it can cause your capacity to be lost by 40 to 50%. Take static pressure very serious and check static pressure on maintenance calls, on repair calls, and after each installation of equipment and or ductwork. Static pressure is critical to heating and air conditioning systems that training technicians and installers on this topic at least 3 times a year is to ensure they get the correct data. It's so very important and vital for companies that want to be successful. Now, furnace and air conditioning units, they rely on airflow inside of their vents to properly intake and outtake air. The total external static pressure, or TESP, is the great indicator of a unit's health. Just like your blood pressure is on a human body, static pressure is the blood pressure of a unit. Okay, and you can pinpoint where the problem is. If it's in my supply, is it dirty coil? Is it no turning vanes? Is it small flex? Flex ain't pulled tight. Where's my resistance coming from? On the return side, do I have a big enough filter? Is my filter dirty? Is my filter in the wrong place? Like I said, on a furnace, that's a 25 by 16 opening. It will carry 2,000 CFMs until you put a filter there. When you put a filter there, you've just condensed it down to a 2.5 ton system. So keep that in mind. I see that more than anything in the world is everybody puts a filter right there at the unit and they're using it for a 3 to 4 to 5 ton drive, and it just will not do it. It'll freeze up every time. So we want to recap, and I want to show you something real quick. Here's what I use out in the field. I have this dual manometer. Here's my zero out button. Make sure you zero out the manometer before you insert the probes, okay? I take these plastic tubing, I put them on here, and I put them on this ductwork. This was for testing your velocity or your speed of your ductwork. The yellow tubes go with these to check my gas probe or my gas pressure. So I'm going to take the clear tubing on these manometers. I'm going to put it here. There's my P1. There's my P2. This is P1. That's P2. So right now, this manometer, see that little dot under P1? I'm reading what's off this would be in my return. And let's say it's showing me that I have a 0.03 and then I have a 0.05. Now, here's what happened. This should be your total. I may be wrong. This may be the total and that may be it, but you'll see the numbers when you pick. Now, if I'm looking at P1 and I see my reading, then if I see a 3, on my P1, I know I have resistance in my return. I should not see a 3 on return. I should see numbers 2, 1, or less. On my supply, which would be P2, then I want to see numbers that may be 3, 4, and 5. If I see a 6, I've got restriction in my supply. If I see a 5, I've got restriction on my supply. So you can look at that real close and see where my problem is. Is it on the supply or is it on the return? The other thing too is also some homeowners will close the vent off because nobody's in that bedroom. That causes static pressure. That causes resistance. So keep that in mind when you go to check your resistance. Make sure if you're in somebody's home, you go through and make sure all the vents are open, the return grills are in place, the turn filters are in, just like the homeowner uses it every day. That's what you're going to have to do to make this work. All right, so when you do this, we're going to recap it real quick what I just said. You got two inputs for pressure. Channel A is supply, channel B is return, channel A is P1, channel B is P2. Make sure you use the rubber tubes and the metal hooks, and then make sure you have zeroed out your manometer. You put A1 or P1 in return. All right, put B2 or P2 in the air handler supply. You can use a 1/4-inch drill, but I think it's a little bit bigger. You can go 3/8. You don't want to go a 1/2 inch, but go 3/8. Fits in and out real good. Do not drill near or top of the heat exchanger. You could damage it, so try to go just past that. You add the two numbers together. Do not subtract them. Add them together. Check your manometer to see what the display is. And like I said, keep in mind that you want to see 3. 3 is too high on return. You want to see 2 and 1 on return or 0. On the supply, you want to see 3, 4, 5. 6 is way too much, okay? 5 is borderline too much because if you're trying to get a overall 0.50, well, then supply can't be 5. Supply would have to be 4 and return would have to be 1. So if you're seeing a 3 on return and a 3 on supply, you know I got to get my return down to at least a 1, so I'm within that 0.50 range. And when you look at some of these install manuals, you're going to see real quick that what they have to have in them. So anything over 0.05 you need to address. And like I told you, you can pinpoint, is it the supply or is it the return? Now, let's say you go to ICP furnaces are usually set. They do not want you at 0.50, anything over that, because you put too much stress on the heat exchanger. And then if you do not have everything done right, you'll have moisture in the heat exchanger. Moisture and static pressure will crack that heat exchanger, and you have the life all the way down to like 6 years. You'll be replacing a heat exchanger on something that should have been 20 years. And if you look at your install manual, ICP is a limited warranty on those heat exchangers. They can say we're not going to cover that because it's put in wrong. So you need to really look at your install manual. There will be a static pressure chart that converts to CFMs. So let's look at it. An air handler is 400 CFMs per ton of the outdoor unit. So if an outdoor unit is a 24 2-ton, that's going to put 24,000 BTU. It's going to put 800 CFM. So that's 2-ton, 800 CFM. A 30 BTU is going to be 1,000 CFM. After checking your static pressure, check the chart for the CFM rating. Once you have figured out the amount of CFM needed, then adjust your speed tap and recheck your static pressure again. If the static pressure cannot be reached within the parameters you need, try opening up the return first, which means make a bigger return grill or maybe adding a return grill. Adding return is better long-term fix than just changing out a filter. Keep in mind compressors fail, X13 blower motors fail, coils fail, heat exchangers fail, all due to high static pressure. If static pressure is too high, you have an evidence of airflow issue. Check for blockage in your ductworks. Maybe the damper's closed. Maybe your flex is kinked. Maybe it's a transition or an offset that's not done properly. Things that you can fix. Maybe you need to change a ductwork fitting. You need to change this. But let's say you're doing a unit swap out. Take the opportunity and think outside the box, because the static pressure will allow you to see the system in a entire new light. Airflow becomes visible when you can read your static pressure and you know where the problem is. You can easily show the homeowner where the problem is and may get some extra work to fix the problem. Now, this new frontier in the duct system, when it comes to value, a properly installed, tested, and balanced duct system is worth far more than a new furnace. What sets you apart from your competition? Well, there's so much competition in the HVAC industry. The only thing that really sets you apart is your ability to design, install, and balance a duct system. It sets you apart from competition. So static pressure measurement unlocks the door to a system as a whole. You can gain access to an amazing amount of duct repair and renovation work from systems you service every day. The margins are extremely high, and the skill required to perform ductwork renovations are minimal compared to being a service tech. It's unfortunate that some in our industry are comfortable attaching new, high efficiency equipment to old, inefficient, and poorly installed duct systems. They just assumed everything will work great. If you are one of them, that could be two massive duct system false assumptions you're making. Let's look at them and see what you might be missing. Who was the original installing contractor responsible for the duct system that you attach your new equipment to? If they're a contractor that you've badmouthed for poor workmanship, well, congratulations. You just joined their club because now you own their duct system. Design only tells you what the intended outcome of an installation should have been. It doesn't ensure the design will work. When you hook up new equipment to another contractor's duct system, you assume that they designed their ducts correctly. A good design allows for ducts to supply and return airflow from the air handler's equipment blower at an acceptable static pressure. These ducts will also deliver the right amount of air to each room, but they aren't self-balancing. So if you believe a 6-inch duct always and carries CFMs, 100 CFMs of airflow, then you should reconsider. Different duct sizes will deliver different airflow volumes based on the length of the run and fitting types you use. You must also consider the installation because that's what determines if the design will work in the field. One thing I see a lot of is contractors come in and they buy 6-inch flex, assuming they need 100 CFMs in a bathroom or a small bedroom. They'll get 6-inch flex and they'll get a 4x10 by 6 boot and a 4x10 floor grill. That 4x10 grill only lets 55 CFMs come through. So you've already created static pressure right there, all right, because it's not going to let the whole 100 come through. You're going to hear it whistling or you're going to hear airflow coming through because the velocity speeds up. So you'll hear it. So you think, okay, well, that velocity is great, but not if it's self-inflicted like that. If you have designed the duct to have the exact same CFM or the right carrying, you will automatically have good velocity. But when you start restricting it down too far, you're going to cause back pressure on the blower motor. So you got to keep that in mind. If someone told you that your duct design and installations didn't work, could you prove them wrong? What could you do or say to defend your workmanship if someone questions the results? Holding your hand over the supply register and proclaiming it blows good isn't enough. I've seen and heard that so many times. Or the best one I've heard is, I've been doing this 30 years. Well, you could be doing it wrong for 30 years because things have changed in the last 5 years. So if you're still doing the same thing you did 30 years ago, it is wrong now. Unfortunately, if a problem arises after you install a new air handler or gas furnace to someone else's duct system, you may need to provide proof of proper operation, while proper duct design is what should have happened. The installation is what really happened. It's a finished product. A few factors to consider in the installation that's put incorrectly are: the ducts are tight and don't leak. All flexible duct is pulled tight, it's straight, and it's supported with no restrictions and no kinks. Duct fittings don't create excessive pressure drops in the duct system. Don't put in a system with a square throat, square back without any turning vanes. Use round pipes or round throats or round heels. Duct insulation prevents excessive temperature losses to unconditioned space like attics or crawl spaces. When you measure, you know. You'll never know how bad these assumptions are unless you test. If you don't test, you're blind to the results of installing new equipment to existing ducts. I once heard, if you don't test a system you hook new equipment to, well, you're no better than the installer who did it wrong in the first place. Keep that in mind. That is so true. When you measure, you can be assured the right amount of airflow makes it to each room. You don't have to guess. You will also know that duct pressures are within design parameters and not double what they should be. When you measure, you know. Do you really want the unknown liability? I heard a guy once say, he has been doing it for 30 years now, So I'm sure it's right when asked what was the static pressure was set. Don't be that guy. I have asked the guy, what did you set the static pressure at? And his words were, well, I've been doing this 30 years, so I'm sure it's done right. Had no idea. Never said it. That let me know it never was tested. Now, let's look at this. Here is the old rule of thumb that we used back in 1994, and it's still pretty close to the same. ICP equipment is set to run at 400 CFM per ton. They would love it at 350, but let's just say 400 CFM is a rule of thumb. Homes with great insulation, that could be spray foam, tight insulation, vapor barriers with insulation, you could get away with 600 CFM, 600 square feet per ton. Decent insulation houses, which is the 80% majority, 500 CFM a ton. But old homes and commercial properties should be 400 CFM a ton. Example, let's say a house is 1,342 square feet and it needs to be conditioned. Well, if I take 1,342 and I divide it by 500, because I'm saying it has a house with decent insulation, I get 2.68. So we're going to call that a 2.5 ton system, 1,000 CFMs. So I take my 1,000 CFMs and I divide it by 1,348, that's what size the house was, and I get a 0.74. That is how much CFMs that house needs per square foot to heat and cool that house properly. Now, some of the super cool slide rules and stuff, they use a 0.80 flat rate. That's what it's at. So you can't go wrong because you're talking about minute numbers. So if you want to go 0.080, that's fine. If you want to go accurate, this is the way you do it, and you'll find out exactly what it is. So now let's say we've got a 12 by 14 bedroom. So we take the 12 by 14, we'll multiply that together, and that's 168 feet. So then we take our 168 feet, multiply it by our 0.74, and we get 125.16 CFM. That's going to be my 7-inch ductwork. Now, you need to look at Ashra's ductwork size because at flex will carry less than what hard pipe is. But if I'm hard piping my duct, I will be able to get 125 CFMs to that room, provided I use a 4x12 grill, because a 4x10 won't let enough in there. And I may have to go bigger than a 4x12. I may have to put a 4x14 in there just to be able to get 125 CFMs to it. So check your grill, whatever grill brand, if it's Honeywell, or not Honeywell, but Hart and Cooley that you're using, check their website and make sure those grills will allow that much CFM to get through it, and before you install it, because you have to make sure I got to get 125 CFM in that room, and I got to pull 125 CFMs out of that room. Okay, so you got to keep that in mind. Whatever I'm putting in, I got to be able to pull back out too. So now we're going to look at our ductwork installs. Square heel, square throat. I did that backwards. Square throat, square heel, no Turner vanes is very poor. Square throat, square heel with Turner vanes is better. But if I've got a radius throat and a radius heel, so much more than is a lot better than even that with Turner vanes. That's the best. Now, same way with a T. Square throat, and I have no turning vanes. Here I've got a radius throat that's better, but a square throat with turning vanes is actually even better than that. But to have a radius heel and a radius throat is best because that's the flow the airway goes anyway. Now, I've seen this quite a bit. This is called a poor man's reducer, where you take a big piece of duct and you stick a little piece of duct in and you put a piece of metal there, or you do this in duct board. And there's no turning vanes, there's no transition. What's going to happen? You're going to have turbulent air right here. So how hard would it have been to come back here and do a line to push this air up and get rid of this whole square? That's called a poor man's reducer, and you will have issues, and that causes static pressure there. Also on your transitions, a center taper transition is always best. Keep in mind, I've seen this here, but in a worse way, where this line here went all the way down to here, and the air was coming out of the unit right here, hitting this and bouncing back. Huge static pressure issue, caused the compressor to almost fail. If he would have had this in here, would never had any problem. So we look at the equivalency of ductwork. Now, here's something I'm going to blow your mind with, because ICP wants you to have 100 feet total ductwork. That's trunk line and flexes. Altogether, 100 feet. So if I took 190 1 square throat 90, square heel, and no turning vanes. Okay? Look what it's equivalent to, 39 feet of ductwork. If I take a square throat and a round heel, radius heel, equivalent to 36 feet of duct. But if I take a radius throat and a square heel, 13 feet of duct, because the air blows in an angle like this, and you'll see turbulence here just like this line's showing. But if I have turning vanes, 4, equivalent to 4 feet of duct. Keep that in mind when you're installing your ductwork and your duct systems, because on round pipe, you want to have a round throat, round heel, and you're going to get the same result. Now, if you figure above by adding turning vanes to 190-degree corner, you see what the equivalent of the feet is, and they want everything to be 100 feet or less. On a large system, the HVAC designer should analyze the entire duct distribution and should be installing turning vanes on critical paths of airflow if you're using square duct. So if you're using round pipe, it's not near as bad. Static pressure is king, so treat it as such. Here's other things that will affect static pressure. I've been in houses and seen this, where this is an older system. Make sure you have those off, because all they're going to do is paddle the air instead of scoop and throw the air. This is a huge issue with static pressure. There's blockage, so that's going to cause resistance. Or flex going under a house over water pipes, smashed up against the floor here. You've pinched that down to 1/3 of its size. That's resistance caused there. Dirty filter, that causes resistance, and in the attic, when this gets hot, that inner liner breaks down and collapses right here, and you can see all the weight from this flex is just dangling here. That's going to cause resistance as well. What affects static pressure? Everything in the system. Ductwork, coil, blower motor, speed. If you don't fix the ductwork, you're no better than the guy who installed it. Units will last if they're installed right. Static pressure is right, CFM is right, duct size is right, and the coils are kept clean. Static pressure is king, so treat it as such.